On this slide, I'm gonna give you a little bit of sense of what the OCB mechanism is like. I'm gonna explain why OCB is affected by the oxide on the wire surface and oxide thickness. When electrical energy is supplied to the bond wire, the bond wire is going to melt, is going to have a molten ball, is going to grow, but the bond wire right next to the molten ball, I would call it a TBMZ, to be melt zone. It's nothing but a solid. Elevated temperature is very hot. When a metal is exposed to the high temperature, is going to experience metal oxidation. This oxide thickness depends upon wire material types and temperature. Of course, if this TBMZ oxide thickness is very small and thin, no problem with OCB. If this TBMZ oxide gets thick, it does not break down gradually during ball formation. Rather than that, for instance, here left hand side oxide layer is long, but it's not broken down yet. But on the other hand, on the right hand side, oxide layer broken down, this would create a no symmetry situation, no axis symmetry situation. Material is symmetric, geometry is symmetric, and the molten ball is symmetric. But broken oxide layer on the surface of the bond wire is not symmetric, so it's going to interfere with the surface tension of the molten ball. That's going to trigger the OCB formation. This whole thing occurs over a very short period of time, so very difficult to provide like a proof of this phenomena. But anyway, so when thickness of oxide is very thin, the little interference with a molten ball surface tension, so there is a stability going on. On the other hand, however, when we apply aluminum coating on the surface of the bond wire in an artificial way, this is nothing but a passivation. So this passivation is not going to allow any additional metal oxidation of the bond wire itself, so that we can control the metal oxidation of the bond wire. As a result, we can control the OCB formation. At the bottom, you are seeing a typical mud crack of a very thin coating. Here, this particular paper describes the stresses in a coating layer as a function of a coating thickness. On this slide, you're seeing a free air ball for the aluminum oxide thickness of like a 0.6 all the way up to 15 nanometer on a 1.1 mil diameter of aluminum, the gold wires. You can, like a bond wire was melted to form a free air ball, and it solidified. And you can see the aggregation of aluminum oxide on the ball because wire was molten, but aluminum oxide was not. The melting point of the aluminum oxide is greater than 2000 degrees C. But however, I want to emphasize this aggregation is not a dirt or contamination of any kind, because this aggregated aluminum oxide can make a good bonding with EMC resin and a ball bonding. So it does not make any degradation in terms of strength. Here I'm showing you bondability data for the 1.1 mil gold wire having an aluminum oxide thickness of 6 nanometer thick, 8 nanometer thick. Fab size is same. Bonded ball size is same. Bonded ball height is the same. And we found the strength is same as well. Wire pull strength, ball shear strength, stitch pull strength. There's a little bit of a drop, but looking at a stitch fracture mode, they are all same. Here, the diameter is 0.7 mil gold wire and a silver wire, almost the same strength were obtained. Aluminum oxide coating does not change IMC types or IMC thickness between wires and pad metals. The resulting IMC surrounds the broken pieces of aluminum oxide. And aluminum oxide has a good adhesion to wire and pad metals. This is why bonding strength is the same for both no coating and coating cases of aluminum oxide. Reliability testing was done for the packages susceptible to wire cut failure mode during accelerated thermal cycles. Very serious temperature swing from -65 all the way up to 150 degrees C. The conventional wire started to fail at 1400 cycles. However, aluminum oxide coated wires survived more than 2000 thermal cycles. Please note that a diameter of the aluminum oxide coated gold wire was much smaller than a bare gold wire cases, 1.7, 1.2. Right now, apple to apple comparison testing is going on, 1.2, 1.2, 1.5 to 1.5. Diameters are the same for both no coating and coating cases of aluminum oxide. For the conclusions, aluminum oxide coating can provide adhesion promoter, insulation, and passivation to conventional bond wires. Adhesion is increased by the introduction of aluminum oxide coating, and aluminum oxide coating enhanced OCB for the silver wire, and I show the same bondability, and the lifetime of the package improved during thermal cycles by making use of aluminum oxide coating. That indicates that we can decrease the diameter of the bond wire, and that a cost reduction is possible. Thank you very much for your attention.